Welcome to the DX Today podcast, where you get facts, not hype. We are diving deep into a topic that it's really fundamentally redefined technology in late 2025. The multimodal revolution.
It really has.
If you're a learner trying to keep pace with, the fastest moving industry on the planet, you know that the last couple of years were characterized almost entirely by large language models, the LLMs.
Right, the text generator.
Exactly, and their ability to generate that incredibly human-sounding text. But the stack of sources we have today confirms that 2025 is the definitive inflection point. It's the necessary structural shift from those text-based foundations to what we're calling native multimodal intelligence.
And that's the crucial distinction right out of the gate. When we talk about native multimodal systems, you have to understand, we are describing an architecture that is fundamentally different from what we had just a year ago.
This isn't just an add-on.
Not at all. It's no longer about engineering teams taking a giant text model and then, bolting on a separate visual adapter or an audio module as a secondary thought. That was the old way.
The 2023, early 2024 way.
The cumbersome, and as we'll see, the inherently limited way of doing things. The frontier models that are defining the market today are engineered from the ground up, from scratch, to reason across text, image, audio, video, and code, all within a single unified parameter space.
So they're taking in raw sensory data.
Exactly, and processing it simultaneously, which profoundly changes their capacity for understanding the world.
And the goal for you, our learner, today is to move beyond that hype and really unpack the core mechanics of this revolution, that foundational architectural shift we're talking about. We're going to identify the players, what we're calling the big three, and see how they are battling it out using entirely new high-stakes benchmarks. But most importantly, we're going beyond the lab reports to look at the massive, measurable impact this is having right now.
In the real world.
In the real world, from optimizing Walmart's massive supply chain to driving breakthroughs in medical diagnostics, all while, understanding the critical challenges.
And there are big ones.
Big ones, like the mutation of the hallucination problem and the escalating copyright wars that are, frankly, trying to pull the brakes on progress.
It truly is a comprehensive look. Understanding the fundamental architecture is the only way to truly understand the why. Why are we seeing these immense performance gains in late 2025?
Right.
This deep dive will give you that essential framework you need to navigate this incredibly fast-moving landscape.
Okay, let's unpack this then. When you look at the performance gains, especially in visual and temporal reasoning, it's so clear that this isn't just about faster chips or, throwing more data at the problem.
No, it's a design revolution, a total rethink.
It's a design revolution.
Yeah.
So let's start with the most critical foundational concept, the difference between the old way and the new way. Late fusion versus early fusion.
This is, without a doubt, the single most important concept for you to grasp. To understand late fusion, which really defined that earlier multimodal era, like GPT-4V, think of it as a modular system.
Okay, separate parts.
Separate parts with a necessary and very restrictive bottleneck. You had two separate specialized brains, so to speak. You had the visual brain, often a specialized vision transformer, a VIT.
And its only job was to look at the picture.
Its only job was to look at the input image. And what did it produce from that?
A summary, right?
A highly, highly compressed summary. It took the entire visual field, all those pixels, and squeezed it down into a dense set of numerical representations. We could call them vectors or embeddings.
Okay.
And those embeddings were then passed through a small network, a little bridge network, sometimes called a Q-former, into the language model.
So it's like a translation step.
It's a translation step, and that step was slow, and more importantly, it was inherently destructive to information.
So if I can use an analogy here.
Yeah.
The LLM wasn't really seeing the picture. It was like trying to edit a movie script after only reading the character descriptions.
That's a perfect analogy.
It's reading a highly condensed, bullet-pointed summary of all the visual data.
You've hit the nail on the head. And that exposes the key problem of late fusion, information loss. It happens right at the encoding stage. If that initial vision encoder missed a subtle detail.
Like what?
Well, maybe some tiny text written at an odd angle on a sign in the background of a photo, or a subtle momentary flicker of a micro-expression on a person's face in a video frame.
Something a human might catch.
Something a human would definitely catch. But if the encoder missed it, that information was lost forever. The LLM, the big reasoning engine, never even got a chance to see the raw detail. It couldn't recover it, no matter how intelligent it was.
So its intelligence was totally constrained by the quality of that compressed secondary summary it was handed.
Completely. It was fundamentally limited.
Wow.
Yeah.
That makes the shift to early fusion, the 2025 paradigm used by the giants like Meta's Llama 4 and Google's Gemini 3 sound, not just like an improvement, but, I mean, a necessary philosophical change in design. How exactly do they pull that unification off?
They eliminate that bottleneck. They just get rid of that translation step entirely.
That's gone.
It's gone. The model is trained from scratch on a massive composite data set. All the modalities, visual patches, text sentences, audio snippets, they're all mixed together from day one.
So when an image or a video frame is fed into the model,
The visual patches are tokenized, just like words. And critically, they are treated mathematically identically to text tokens right from the earliest transformer layers.
so there's no separate vision encoder trying to summarize the picture first.
None. There's one unified neural space.
So the visual information and the textual information are interacting from the very beginning. They're informing each other's processing, creating these deep cross-modal correlations, starting at layer 1 of the network.
Yes.
This is why we call it native intelligence.
It is the very definition of native intelligence. And the sources, they really emphasize that the implications for reasoning are just profound.
Give me an example.
Okay, take a task that requires temporal reasoning in video. An early fusion model can understand the temporal cause and effect. It can trace the trajectory of a ball across multiple frames and deduce the impending collision before it happens.
It understands why a glass is about to break.
Exactly. It understands the physics. A late fusion model would just identify the entities, a ball, a glass, and then later broken glass. But it would really struggle to grasp the physics and the temporal relationship between those objects.
Got a huge difference.
It's a night and day difference. Furthermore, and this is a huge economic point, the research shows that early fusion is often more efficient to train.
More efficient.
Yep. And it can yield stronger performance at lower parameter counts. This efficiency is precisely what allows models like the smaller Llama 4 Scout to be so incredibly performant.
That efficiency aspect, that leads us perfectly into the next architectural cornerstone.
Yeah.
Managing the sheer scale of all this data and, all those parameters using the mixture of experts, or MOE, we are essentially incorporating the entire sensory world now. So the computational cost must be astronomical.
It is. It's astronomical. The challenge is that as models grow to incorporate more modalities, more vision, more audio, more cold, the computational cost for a dense model.
And by dense, you mean every part of the model is active all the time.
Every single parameter is active for every single calculation. That model skyrockets to an economically unviable degree. It's just too expensive to run. So MOE is the industry's universal answer to this density problem.
Okay.
It shifts the paradigm from dense models to sparse models, where only a small, specific fraction of the network is actually engaged for any given query.
And we have a fantastic example in the source material for this, Llama 4 Maverick. Help us understand the scale of MOE here.
Llama 4 Maverick is cited as having this massive total capacity. We're talking 400 billion total parameters across 128 distinct experts.
128 experts.
Yeah, and you can think of these experts as highly specialized knowledge pods. So one expert might be the world's foremost authority on 17th century French poetry. Another one might specialize in diagnosing Postgresql database errors.
Very specific.
Incredibly specific. However, when you, the user, submit a single token, a word, or a visual patch from an image, the model's routing network intelligently activates only a small subset of those experts.
All 128.
Oh no, maybe just 4-8 of them. And it picks the most relevant ones for that specific inference calculation.
So this means the model has this massive, diverse knowledge base of 400 billion parameters to draw from, but it runs with the speed and the cost efficiency of a much, much smaller active model, maybe only 17 billion active parameters.
That's it.
This is the definition of being able to deliver massive capability at a reduced cost.
Absolutely. It democratizes the use of these massive models. And the routing intelligence itself has become highly advanced. We're seeing the evolution of what's called modality agnostic routing.
What does that mean?
It means the router doesn't just look at the input type, is this text or is this an image? It looks at the content and the task.
Okay, so give me an example.
Let's say you input a piece of Python code that deals with geometric calculations. The model might smartly send that text token not just to the code expert, but also to the spatial reasoning expert, which might have originally been trained primarily on visual data.
That's intelligence layering on top of intelligence. The routing network is its own AI.
It has to be.
And we see this sophisticated routing applied at the system level, too, in what the sources call router AI within the GPT 5.1 family. This seems critical for the bottom line.
It's the absolute foundation of their economic strategy. GPT 5.1 employs an intelligent, automatic routing layer that serves as the economic gatekeeper. It analyzes the complexity of your prompt before it sends it for expensive processing.
So a simple prompt like, summarize the news headlines from this morning, which is pretty low compute.
That gets instantly routed to the low-cost, high-speed GPT 5.1 instant model. Quick, cheap, and efficient.
But if the prompt requires serious high-stakes multimodal reasoning, say, analyze this complex physics diagram, cross-reference it with these 3 supporting research papers, and generate a simulation script in Julia code, that's when the router AI sends it to the big guns.
Exactly. It sends it to the compute-intensive, high-latency GPT 5.1 thinking model.
Right.
And this tiered approach is mandatory for scale and profitability. It ensures you get the right amount of compute power for the complexity of the task, and OpenAI saves massive amounts of money by not using their most expensive thinking resources for simple chat queries.
It makes perfect sense. A crucial development for economic viability at enterprise scale.
For sure.
And finally, for multimodal AI to truly feel conversational, it had to master the fluidity of human speech. And that brings us to continuous tokenization. We lost so much nuance in the old systems, didn't we?
Well, we did. Traditional models discretized audio, which means they chopped the raw waveform into segments and tried to represent those segments as discrete text-like tokens.
And in that process, you lose the human element.
Yeah. You strip away the very human elements, the paralinguistic features, things like tone, emotion, hesitation, speaker identity. The model could understand the words, but not the intent.
So someone said, I'm fine, with a clear tone of sarcasm or distress. The old model would only register the text token, fine.
Exactly. It was deaf to the music of the language. The breakthrough lies in new architectures, like the one exemplified by Flow Omni, which utilize continuous valued speech tokens.
Continuous value?
Yes. Instead of converting the audio into text tokens, these models process the raw waveform or continuous representation of it, preserving all those critical paralinguistic features. They are inherently designed to understand not just what you say, but how you say it.
This is the difference between a robotic transcription service and a genuine conversational understanding of human intent.
It's a massive leap.
And this architectural advance enables the fundamental user impact we're now seeing in models like Gemini 2.53 and GPT-405, bidirectional streaming and interruptibility.
And this is perhaps the greatest quality of life improvement for the user. Bidirectional streaming means the AI is processing your audio while you are speaking. It's not just waiting for you to finish your turn.
And interruptibility.
That means you can cut off the AI mid-sentence just like you would in a natural human exchange, and the model instantly registers that interruption, adjusts its response, and begins speaking immediately.
No more awkward pauses?
No.
Yeah.
It fundamentally changes the user experience, moving the AI from being a turn-based system to a seamless, continuous conversational partner. The latency drop here is essential for large-scale adoption in customer service and personal assistance agents.
Here's where it gets really interesting for me. We've talked about the mechanics, the early fusion, the MOE, the continuous audio that allows for true dialogue. These architectural shifts, they determined who won the competitive battle.
Right.
So now let's look at the current battlefield, which is defined by the big 3, and the specific metrics they're using to differentiate themselves. The days of winning based on who just has the largest, densest model are definitely over.
They're long gone. The competitive landscape of late 2025 is a fierce, well-defined tripartite struggle. It's dominated by Google DeepMind, OpenAI, and Meta. And each one has chosen a very specific strategic vector for differentiation, largely built on their unique architectural strengths.
Okay, let's start with Google DeepMind and Gemini 3. Their strategy seems laser-focused on integration and leveraging truly massive context windows for superior long-context reasoning.
That's their calling, card depth and memory. The Gemini 3 family is built to emphasize seamless multimodal integration with staggering context windows. The Pro model handles over 2 million tokens.
2 million tokens. Let's put that scale into perspective for the listener. What does that mean?
2 million tokens is equivalent to processing a 1,500-page book in a single prompt, or about 50 hours of audio.
Wow.
So Gemini 3 Pro has become the established benchmark leader in tasks that require deep, complex, cross-modal reasoning over massive datasets. Think legal discovery or complex scientific review.
And the sources point out that this model incorporates a visible thinking process, which is highly unusual.
It's a key feature. Before generating a final answer, Gemini 3 Pro can utilize a multi-step deliberation feature. It pauses, often visibly in the interface, to deliberate on complex visual inputs.
Like what?
Like analyzing a nuanced physics diagram or systematically debugging a huge block of code from a screen recording. It thinks before it speaks, and they show you that process. They are essentially monetizing the ability to perform complex, transparent System 2 type of thought processes.
And the key metrics confirm this focus on high-level scientific intelligence, right?
Absolutely. The performance on the GPQA dataset, that's the graduate-level Google Proof Q&A, is definitive. Gemini 3 Pro achieves a score of 91.9%.
And these questions are written by PhDs.
Yes, specifically designed to be unanswerable by a simple search or knowledge retrieval. You have to synthesize disparate concepts to get the answer. That 91.9% score positions Google clearly at the top for pure, expert-level scientific reasoning.
And that huge context length must give them an edge in video.
A huge, almost insurmountable edge in video MME, which is the benchmark for long-form temporal comprehension. They leverage that 2 million token window to process up to an hour of high-fidelity video in one go.
And their ecosystem, it seems engineered for deployment efficiency. They're covering the entire market.
Precisely. They have the massive, expensive Gemini 3 Pro for the really tough jobs, but then they deploy Gemini 2.5 Flash for high-volume, low-latency voice agents and the ultra-efficient flashlight for edge deployment.
So no matter the hardware constraint or the complexity, they have a tailor-made model.
That's the strategy.
Okay, switching gears to OpenAI's GPT-5 evolution. Their strategy seems less about building one monolithic brain and more about creating a diverse portfolio of specialized high-accuracy agents.
That's the strategic pivot. The release of GPT 5.1 marked a clear shift towards reliability and specialized reasoning. They're consciously moving away from a generalized creative-first approach.
So GPT 5.1 thinking is their specialist.
It's their System 2 specialist, engineered for deep, auditable tasks like financial modeling, legal analysis, and complex coding synthesis. And crucially, it features a partially visible chain of thought capability.
How does that visible chain of thought help the professional user?
It turns the model from a black box into a collaborator. You can actually see the model's intermediate reasoning steps, its hypothesis, its attempts, its internal tool usage.
So you can course correct it.
You can audit and correct the model if it starts to stray during a long, complex generation task. This is an indispensable feature for high-stakes, high-accuracy professional tasks, especially in regulated fields.
And we also see the deep integration of their generative media capabilities into the core product line.
Yeah, the Sora 2 integration is complete. Their leading text-to-video model now functions almost as a native extension of the core GPT product. It provides 1080p output and perfectly synchronized audio.
And the key advantage for users.
The key operational advantage is video-to-video editing. You can take existing user-uploaded footage and just remix it, extend it, or apply highly detailed stylistic transfers seamlessly. This cements Sora 2 as a genuine production workflow tool, not just a cool demo model.
Now let's talk about the true disruptor of the market, the open weight revolution. We're talking about Meta and the Llama 4 family. They introduced that crucial early fusion architecture to the masses, which has massive implications for enterprise costs and especially for data privacy.
Llama 4 is the tectonic plate shift of 2025. You've got Llama 4 Scout, which is the 17 billion parameter model for efficiency, and the larger MoE variant Maverick. The sheer power of Scout lies in its context window.
What are we talking about here?
Up to a theoretical 10 million tokens.
10 million tokens. That scale is difficult to grasp. What does that mean for the average enterprise user or researcher? What can you actually do with that?
It means they have fundamentally altered the economics and the architecture of retrieval augmented generation, or RE systems.
Explain ARAG for the listener.
Okay, so RAG previously involved a complex pipeline. First, you had an indexer that broke your documents into chunks. Second, you had an expensive vector database retrieval step, which used embeddings to find the most relevant chunks. And third, the model generated the answer based on those chunks.
And that middle step, the retrieval, was complex and often introduced latency.
Very. So If Llama 4 can ingest an entire legal archive, a full 10-year corporate database, or a complex code base in a single prompt,
You just don't need the vector database.
for those datasets, you eliminate the need for that complex, expensive retrieval layer entirely.
So you've just made the whole system simpler.
You've hit the nail on the head. For any small to medium dataset that fits within 10 million tokens, the infinite context capability essentially obsoletes the most expensive part of the RAG pipeline.
Simpler architecture, lower latency, reduced complexity.
And because Meta maintains an open source strategy, they release the weights privacy-sensitive enterprises in highly regulated industries like finance or healthcare can deploy this state-of-the-art multimodal AI on-premise,
So it runs on their own hardware.
often running efficiently on their own existing hardware, which is a massive win for compliance and data security.
This technological leap has naturally forced a corresponding shift in what is considered state-of-the-art in the industry. Let's drill into the benchmark wars. We've heard MMLU is saturated, meaning general knowledge is, for the most part, solved.
MMLU was the 2024 gold standard. By late 2025, models like GPT-5 and Gemini 3 are scoring north of 90%. It proves that general academic knowledge retrieval is effectively a solved problem.
So the goalposts have moved.
The battleground has shifted entirely to expert-level tests that require deep reasoning, synthesis, and problem-solving, not just fact recall.
We discussed GPQA graduate science reasoning, where Gemini 3 Pro leads at 91.9%.
Yeah.
But what about the true measure of autonomy, the ability of these AIs to act as autonomous developers, fixing bugs in the wild?
That's the utility of SWE Bench. And this isn't theoretical code generation. It tests autonomous coding ability by challenging the AI to solve real, documented GitHub issues.
Real bugs.
Real bugs and feature requests found in actual open source repositories. To succeed, the model has to navigate a live code base, understand the context of the bug report, and then write and apply a functional patch.
And who's leading there?
Here we see Claude Opus 4.5 leading with 80.9%, though the others are very close behind. This metric is the true measure of an autonomous coding agent. It's about practical application.
And the final piece is saturation. Math. The source data shows something truly remarkable, that advanced mathematical reasoning is now effectively solved.
It's staggering. I mean, it really is. Models like Kimi K2 Thinking, Grok 4 Heavy, and Gemini 3 Pro have all achieved a perfect 100% score on the AIM 2025 benchmark.
And AIM is not simple arithmetic.
No, 80 is the American Invitational Mathematics Examination. It requires Olympiad-level math and intricate multi-step problem solving. This confirms that the chain-of-thought reasoning and precision capabilities in these frontier models can handle the complexity required for advanced mathematics.
It's staggering that math is solved, but the complexity of temporal reasoning still requires these brute force context windows. It shows us exactly where the limits of intelligence still lie. Let's revisit the need for long context with the Video MME benchmark.
Right. Video MME tests temporal reasoning. That's the ability to understand sequences, causality, and complex state changes over long spans of time in a video.
And this is where Gemini's huge context window pays off.
It's why it dominates, because Gemini 3 Pro's 2 million token context window allows it to ingest up to an hour of video with continuity. It dominates here with scores above 75.0%. This capability is essential for any application that needs to understand a continuous stream of events.
Like what?
Industrial monitoring, medical diagnosis from long-form scans, or autonomous driving. Anything where the past informs the present.
If we connect this architectural and competitive analysis to the bigger picture, the conclusion seems pretty clear. These technical leaps, the native multimodality, the MOE efficiency, the massive context, they are now driving massive, measurable, and monetizable changes in enterprise workflows and creative industries.
Exactly. This shift isn't theoretical anymore. It is the utility engine of late 2025.
Let's start with the most visible part of this change, the generative media wars. Video generation has moved way beyond novelty, but it's fragmented heavily. Providers are specializing in distinct niches.
That fragmentation is crucial because the market has matured. We have 3 major niche leaders, and each excels at a different aspect of video synthesis.
Okay, let's break them down. First, OpenAI's Sora 2.
Sora 2 is focused heavily on physics realism. It's engineered not just to make pretty pictures move, but to understand fluid dynamics, gravity, and object collision.
So it's about simulation.
It's incredibly powerful for world simulation and consistency, which are essential features for things like level 5 autonomy and game development. Its key features are the remix capability and, crucially, consistent cameo character generation across multiple clips.
Which solves that continuity problem.
It solves the narrative continuity problem that plagued earlier models. You can have the same character appear in multiple different scenes.
So Sora is focused on how the world works, who has cornered the market on how the camera works.
That would be Google's VO3. It's deeply integrated into the creator ecosystem, so VO3 excels in cinematic camera semantics.
What does that mean in practice?
It means it's optimized for the creator economy and YouTube B-roll. It allows users to prompt specific, complex camera moves with high precision. You can give it commands like execute a perfect dolly zoom, truck left while maintaining focus, or perform a clean rack focus from foreground to background.
So it's for generating polished, professional-grade visual assets with high cinematic fidelity. And then you have the third niche, focused purely on giving the professional artist maximum control over the output.
And that's the enduring strength of Runway Gen 34. They continue to lead in creative control. While Sora pursues realism, Runway focuses on steerability for the professional VFX artist.
So less about automatic realism, more about manual artistry.
Exactly. They offer director mode tools like motion brushes that give artists granular, pixel-level control over specific elements, movements, and trajectories. If you need precise artistic control over every element, regardless of realistic physics, Runway is still the tool of choice.
Beyond video, we've seen a rapid audio renaissance, moving us from that slow, robotic text-to-speech to human-quality, real-time speech-to-speech, or S2S, modeling.
And this ties directly back to our architectural discussion on continuous tokenization and low latency. Gemini 2.5 Flash has quickly become the enterprise favorite for voice agents.
Why them?
Because of its incredibly low latency, which is crucial for real-time interaction, and its native speech understanding. Because it processes the raw waveform, it handles complex languages like Chinese exceptionally well, correctly placing prosody and pauses without needing a perfectly transcribed text input first.
And the interruptibility.
And its interruptibility makes it ideal for seamless, high-volume customer service applications.
And then you have the creative specialist in audio. 11 Labs.
11 Labs V3 remains the unchallenged gold standard for pure voice cloning and maximizing emotional range. They've made a really smart pivot, transforming from a simple TTS engine into a comprehensive audio platform.
A platform?
Yeah, they're now integrating sound effects and music generation. They are focused on creative production, things like audiobooks, gaming, and narrative content, while Gemini 2.5 Flash focuses on enterprise real-time utility.
Now let's look at the true engine of change in the corporate world. Enterprise transformation. The conversation has shifted dramatically from using chatbots to deploying sophisticated autonomous agents. The source notes that a staggering 79% of organizations are adopting AI agents to some extent.
And we must be crystal clear about this agentic shift. A simple chatbot just responds to input. An agent, what we sometimes call a super agent, performs a multi-step workflow toward a goal.
So it does more than just talk.
Much more. It breaks a large task into sequential subtasks. It uses tools, it accesses APIs, external databases, it sees the screen or the physical environment via multimodal inputs, and it acts.
It executes clicks, keystrokes, sends emails.
Exactly. This ability to execute multi-step workflows with minimal human intervention is the critical element transforming major industries.
Let's examine the two critical case studies provided in the sources, starting with retail and supply chain, the massive operational efficiency gains at Walmart.
Walmart is a textbook example of agentic multimodal AI deployment across its vast supply chain. First, let's look at visual inventory management. They deploy an array of cameras and vision agents, often powered by highly customized Llama 4 equivalents, throughout their distribution centers and stores.
And these systems are doing real-time quality control.
All the time. The AI is constantly inspecting pallet stacking for stability, looking for subtle damage on boxes, or analyzing the quality of produce.
Can you give us an operational detail here? What specific visual anomalies are these agents catching that a human might miss in a quick scan?
They're catching things like inconsistent lighting that might hide a defective seal on a package, mislabeled expiration dates that are too small for a quick human scan, and complex geometric stacking anomalies like a pallet stack just 5 degrees off center that could lead to a massive collapse during transit.
And the AI flags this immediately.
Immediately, often before the pallet even leaves the warehouse. This is a massive leap in proactive quality assurance.
And this data then feeds into the second operational change, dynamic task prioritization.
Yes. And this is where the agentic part really comes in. The AI doesn't just spot the problem, it drives the solution. Store associates use an AI-powered app that generates tasks based on this real-time multimodal data.
Give me an example of a task.
Okay, so if the AI sees, via inventory data and incoming shipment schedules, that a large volume of perishable item X is arriving and shelf Y is currently cluttered, the agent automatically generates a specific prioritized task for a specific associate. Clear shelf Y by 4:00 p.m. for item X stocking.
And this is saving managers a lot of time.
It reduces shift planning time for managers from 90 minutes down to just 30 minutes. It's shifting operations from being predictive to being truly agentic.
That integration of visual data directly into human action is even more complex in manufacturing, using the concept of the industrial metaverse, championed by Siemens.
Siemens is heavily leveraging digital twin technology, which is a perfect use case for multimodality. They run systems that continuously compare a live video feed of the factory floor against the perfect digital twin of that factory, a highly detailed, accurate virtual model.
So the AI is looking for differences.
It's designed to instantly spot deviations. A leaking pipe that shows up as an unexpected visual anomaly. A vibrating motor that is simultaneously registering a high audio frequency and a visual wobble. Or a robotic arm that is misaligned by a fraction of a millimeter.
And the way engineers interact with the factory floor is evolving from traditional dashboards to a more natural exchange.
It's true. Multimodal interaction. Engineers are moving beyond keyboards. They can literally chat with their factory using voice and even gesture recognition.
Asking complex queries.
Very complex, synthesized queries like, show me the real-time efficiency impact on the overall output if we replace this specific turbine with the new model. And the AI generates a real-time visual simulation right there in the digital twin environment.
It democratizes access to incredibly complex engineering data and high-stakes simulation.
It really does.
Finally, in the domain of software, the shift to agents has created a huge quantifiable time saver in coding and debugging.
Agentic debugging is profoundly impactful. The multimodal capability of models like Gemini 3 allows them to use cross-modal input to solve problems exponentially faster than a human engineer.
How did that work?
For example, an engineer submits two things to the agent. A screen recording of a bug occurring, that's the video input, and the corresponding log files detailing the system state, which is the massive text input.
So it gets the what and the why at the same time.
Exactly. The multimodal agent watches the bug, analyzes the log files against that visual context, and then suggests a specific targeted code fix. This capability speeds up QA and development cycles dramatically. We're seeing reports of AI-assisted development teams generating hundreds of thousands of high-quality lines of code in single deployments.
So what does this all mean? With all this soaring capability comes inevitable complexity and, significant risk. If we're to understand the true adoption rate, we have to address the headwinds facing the industry, particularly in safety, intellectual property, and cost structures.
The first critical headwind is the safety issue, and it's evolved into something far more insidious than simple fabrication. We're calling it the hallucination mutation.
The source material refers to a safety paradox. Explain that for the learner. Why does greater accuracy lead to greater risk?
The safety paradox is an issue of trust versus failure rate. As these multimodal models approach near-perfect accuracy, let's say 99.9% human vigilance drops.
We get complacent.
We start trusting the system implicitly for complex tasks. This means the remaining 0.1% of errors, those rare hallucinations, are often unchecked and they occur in high-stakes situations.
Like a complex legal summary or an agentic code fix.
Right, and the consequences of that rare failure are magnified because the human safety net has been withdrawn.
And how has the hallucination problem specifically mutated in the multimodal context? It's not just making up facts anymore, is it?
No, it mutates by filling in the gaps with fabricated temporal or spatial relationships. In video analysis, for instance, if a video shows a person holding a cup and then the scene instantly cuts to the cup already placed on a table,
there's a missing action.
A multimodal model might hallucinate the action of the person reaching out and placing the cup down, even if that specific action sequence was never captured in the frames. It fabricates plausible but entirely non-existent actions.
And we now have benchmarks specifically designed to catch this relational fabrication.
We do. Benchmarks like RAH bench, that's the relational attribute hallucination benchmark, are specifically designed to quantify these errors. RAH Bench focuses on fabricating relationships between objects. For instance, the model claiming person A is standing next to person B when the video clearly shows they are on opposite sides of a room.
And that's a crucial metric for applications like security and manufacturing.
Anywhere where accurate spatiotemporal relationships are paramount.
And the issue of citation failures persists, even with advanced models built for knowledge retrieval and grounding.
Absolutely. The research cites examples like advanced models, including Grok 3, hallucinating sources up to 94% of the time in specific stress tests that push the model toward niche or complex queries.
So it's not just making up a fact, it's making up the source for the fact.
It's fabricating a non-existent URL or academic paper to support an otherwise plausible statement. And this is a massive risk for any professional user relying on the AI for research, legal summaries, or medical documentation that requires auditable fact-checking.
That reliance on external proprietary data brings us directly to the legal battlefield. The copyright wars have escalated far beyond simple infringement claims over training data.
Oh, yeah. The landmark case, NYTV OpenAI, is no longer just a simple dispute over fair use of news articles. It spiraled into a serious data privacy and international compliance conflict in mid-2025.
What happened?
A key court order required OpenAI to preserve specific ChatGPT conversation logs for discovery in the U.S. litigation. This immediately put them at odds with their established data deletion policies and, critically, with stringent EU privacy laws like GDPR.
So the litigation itself forced a crisis point between U.S. legal discovery requirements and international privacy compliance obligations. That's a massive strategic hurdle.
It creates an almost impossible operating environment for global companies. And separately, we're seeing the rise of the parasitic use argument, exemplified by publishers suing search-integrated models like Perplexity.
What's the argument there?
Publishers argue that when a model provides a comprehensive REG summary of a copyrighted article, giving you the answer instantly, it destroys the entire economic model of journalism by bypassing the essential click-through.
So it strips the original creator of traffic and ad revenue.
Exactly. It strikes at the core of the financial viability of information creation itself.
And how is global regulation, particularly the EU AI Act, shaping deployment strategies for these global companies?
The EU AI Act is forcing a strategic bifurcation in product rollouts. Take watermarking, for instance. The Act mandates that all AI-generated content, audio, video, and image must carry machine-readable watermarks, adhering to international standards like C2PA.
Which is designed to combat deepfakes.
Right, and it requires enormous engineering effort for compliance. If a model fails to watermark, it can't legally operate in the EU market for high-risk applications. And the second major requirement involves transparency. Providers of general-purpose AI, or GPAI, must publish detailed summaries of their entire training content.
That must clash with trade secrets.
It's in direct conflict with the U.S. tech industry's long-standing trade secret practices, where training data is often the most closely guarded intellectual property. This conflict between mandatory public transparency and IP protection is leading to inevitable delayed feature rollouts in the EU compared to the U.S. market.
It's a compliance minefield.
It really is.
Let's end this section on a positive note. The economics of efficiency. Despite the soaring cost to train these massive frontier models, the cost to run them, the inference cost, has collapsed dramatically.
The data is truly staggering. The cost to run an equivalent model to what was state-of-the-art in late 2022, say, a robust GPT 3.5, has dropped over 280-fold.
280 times cheaper.
Yep. And this is the direct result of architectural innovations like MOE, allowing for sparse computation, combined with ferocious hardware competition. NVIDIA is now facing strong competition from Google's dedicated Trillium TPUs, Amazon's Trainium, and Microsoft's Maya chips.
Which is driving down compute prices for inference across the board.
It is.
And this cost collapse makes the hybrid infrastructure strategy, that three-tiered approach, the new enterprise standard.
It has to be. No company can afford to run every simple internal query on a $10 per query GPT-5 thinking model. It's just not viable.
So they use an intelligent router.
Sophisticated enterprises use an intelligent routing layer to balance cost and performance across three strategic tiers. Tier 1, complex tasks, the tough, System 2 reasoning queries, are routed to the most expensive, most powerful external models like Gemini 3 Pro, low volume, high cost.
In Tier 2, routine tasks.
Yeah.
The high volume general queries.
Those go to the fast, low-cost external models like GPT 5.1 Instant, high volume, low cost.
And critically, Tier 3, sensitive.
All private data, proprietary information, and internal legal archives that gets processed by self-hosted open-source models like Llama 4 or Mistral, deployed entirely on private clouds or on-premise hardware.
A fixed capital expenditure.
Right. It provides maximum data privacy and absolute control over the data lifecycle, which is essential for regulated industries.
This tiered approach gives the enterprise learner exactly what they need: high performance for hard tasks, low cost for routine tasks, and maximum data privacy and control for sensitive internal information. It's the mandatory blueprint for deploying multimodal AI at scale today.
It really is.
So let's look toward the next horizon, where this deep dive into multimodal architecture and agency leads us. The trajectory for 2026 points inevitably toward greater autonomy, hyper-specialization, and deep integration into the physical world.
I think that's right.
One of the clearest trends is the rise of vertical AI. General models, for all their power, are starting to face competition from systems that are fine-tuned for specialized, compliant industries.
General-purpose models, no matter how good they get, simply cannot compete on compliance or domain-specific accuracy with systems fine-tuned on compliant proprietary data.
So we'll see the dominance of vertical AI.
Absolutely. Models build on open-weight foundations like Llama 4, but exclusively trained and deployed using millions of proprietary sector-specific data sets in law, medicine, or complex finance. These vertical models will offer superior auditability, compliance, and performance compared to generic models.
Especially in high-stakes regulatory environments where accuracy is legally mandated. The second, and perhaps most exciting trajectory, is the shift from digital to physical, embodied AI. The multimodal capabilities we've discussed, native video understanding, physics simulation, are leaving the screen and entering the world of robotics.
This is the logical, physical extension of what we've achieved in the digital domain. The fact that a model like Sora 2 can be trained to understand fluid dynamics and spatial relationships means that intelligence can be directly applied to robotics without laborious, explicit coding.
So embodied AI allows robots to learn from watching.
It allows robots to learn general-purpose tasks like setting a table, assembling a complex component, or organizing a warehouse simply by observing video demonstrations rather than requiring complex, explicit code for every new task.
Which dramatically accelerates the deployment of general-purpose robots in unstructured environments.
It's a huge step forward.
This all suggests that these AIs are developing something that resembles a genuine understanding of the physical world itself.
They are evolving toward the era of world models. Historically, AIs predicted the next token in a sequence. Now, they are striving to predict the next state of the world.
An internal physics engine.
By training on massive volumes of temporal video data, models like Sora 2 and Gemini 3 are beginning to build an internal physics engine, a cognitive model of how the physical universe, including objects, gravity, and fluid dynamics, operates.
And this capability is not just for generating cool videos.
Not at all. It is essential for achieving true Level 5 autonomy in vehicles and for creating fully immersive, self-consistent virtual worlds for large-scale simulation and training.
To summarize our deep dive for you, the learner. The year 2025 was defined by the structural shift to native multimodal intelligence. The architectural leap to early fusion unlocked unprecedented reasoning power.
Which is being efficiently managed by a mixture of expert MOE systems like Llama 4 Maverick.
Right, and the new benchmarks confirm AI is solving complex scientific and math problems, with Gemini 3 Pro leading on graduate-level reasoning and models demonstrating 100% accuracy on Olympiad-level math.
And we are seeing these capabilities applied across the board. Autonomous agents are rapidly transforming retail and manufacturing, turning raw multimodal data into measurable, proactive action.
Evidenced by Walmart's dynamic supply chain management and Siemens' industrial metaverse.
Exactly.
But the path forward is fragile. The ultimate success in 2026 won't be defined by the model with the highest parameter count, will it?
No, it will be defined by the companies and users who can successfully navigate the legal friction, that clash between global privacy laws and U.S. discovery, mitigate the hallucination risk that mutates in the multimodal space.
And strategically weave these multimodal agents into the fabric of their daily operations, turning abstract intelligence into demonstrable action.
That is the ultimate strategic challenge.
And here is a final provocative thought for you to consider. Think about the implications of the infinite context window enabled by Llama 4, allowing for 10 million tokens of data ingestion.
It's a staggering number.
If an AI can ingest and recall every single word of a massive legal archive or an entire corporate code base instantly and perfectly, how fundamentally does that change the human requirement for information retrieval?
That's a good question.
If the AI holds all the context and performs all the retrieval perfectly, what does the human specialist truly specialize in now? Is it curation, critical judgment, or something entirely new?
Something to ponder as you move forward in the era of native multimodal intelligence.
We'll see you on the next deep dive.